Hey, Dina.
Hello, can you hear me okay?
Yeah, I think so. You should be ready to start whenever you feel like it's a good time.
All right. Well, we're a little early today, so we'll wait another minute. All right, so let's get going with a few quick announcements. I hope you guys all had a nice weekend and you are staying healthy and safe and all those things. A couple just quick things. So as a reminder, we had our first chapter quiz yesterday. So hopefully that gave you a sense of sort of the structure of the class. So everything else sort of marches along the same way. So we have mini quizzes for each of the sections. And then at the end of chapter 2, we'll have another chapter quiz. And then we'll have mini quizzes all through chapter 3. And at the end of chapter 3, we'll have a chapter quiz, so on and so forth, marching through the rest of the chapters. So now that you sort of have a sense of how that works, hopefully you feel pretty good about how you did. And if you didn't, then we can certainly go over your quiz during drop-in help or anything like that. So I just want to sort of applaud you for all the work you've been doing. So the way that this course is structured, which is important to me, is that there's sort of a lot of low stakes assignments so that if you mess something up, it doesn't completely, destroy your grade and undermine what you know and all those sorts of things. And so it's just sort of a lot in frequency, but hopefully not too stressful in terms of preparing to do this the way that we're doing it. So you're demonstrating your knowledge in a lot of ways. So through mini quizzes and through homework and through chapter quizzes, and hopefully you're feeling pretty good about the work that you're doing. So this week we are just continuing into chapter 2. Today we're going to be doing 2.1. And I want to sort of set the scene that in chapter 1, we were doing a lot of what's called review work, but we know historically that some of the topics we talk about in chapter 1, some people have never seen, and some of the topics from chapter 1 are things you may not have done for a long time. So that's why we sort of pulled those particular ones out to make sure we reviewed them. However, starting in chapter 2, we sort of assume that you don't know any of the stuff that we're doing, and it's a lot more connected, so it sort of builds upon itself as we go. So it's a little less sort of wide in terms of what we cover. So just as sort of a jumping off point, in math, the way that we construct new knowledge is to think about what we know and leverage it to figure out what we don't know. And so the one sort of big thing that we assume you know coming into this class that we build upon is about lines. So y equals mx plus b. So if you're comfortable with the idea of y equals mx plus b, that's sort of where we start building, right? We've already built one block onto that, which I'll review in a few minutes, but this idea of the pieces of a line and specifically the slope of a line is where we sort of go from here. So I'm going to switch over to the DocCam here. Okay. And so what we're going to be talking about today is called the instantaneous rate of change. And so I want to circle back again to this idea of what we know. So y equals mx plus b, specifically the m, we know is the slope of the line. So the slope of a line is a rate of change, right? It tells us how much it changes in the dependent direction for every 1 unit we move in the independent direction. That's called the slope, the change in y over the change in x. So what we want to do is we want to take this idea of slope and instantaneous rate of change and figure out how we build up to it. So the first thing that we did with this idea of slope and y equals mx plus b is we talked about the average rate of change. So that was back in chapter 1. And what the average rate of change did for us is it took a function that was not linear and said, hey, if you want to approximate how much this function changes on average between 2 points, we can draw in the line to connect those points and find the slope of the line because we know how to find slope, right? So that's what we're sort of leveraging here. So when we did the average rate of change, right, the way we did it is we drew in what was called a secant line, which connected 2 points. So if we wanted to approximate, I don't know, we have some function and we want to approximate how much it changes between 2 points, we would draw a line between those 2 points and find the slope because we know how to find slope. So that was called a secant line that connects 2 points. And so the formula that we used for that was f of b minus f of a over b minus a, which is the same thing as change in y over change in x. And so we were finding the slope of the secant line to make that approximation. So that's the process that we're going to be using to get to our next step. So today what we're talking about is called the instantaneous rate of change. And so what we're trying to do is figure out how we can go from approximating the rate of change between 2 points to figuring out how the function changes at 1 point. So if we can figure out how much a function is changing at 1 point, we can then find out how much is changing at every point and get an exact measure of rate of change instead of an average rate of change, right? So that's our goal, to be able to figure out how much a function changes at 1 point. But again, we need to leverage what we know how to do, which is finding the average rate of change, to figure out a way to get to what we don't know how to find yet, which is the instantaneous rate of change. So just to give you sort of a conceptual idea about the difference, right? So consider that it takes you 3 hours to drive 150 miles to your cousin's house. Okay, so your cousin lives 150 miles away and it takes you 3 hours to get there. Your average rate of change is 50 miles per hour, right? 3 hours, 150 miles, 50 miles per hour. Your instantaneous rate of change, however, is the reading on your odometer at any given moment. So we know that you weren't driving 50 miles per hour the entire time. Sometimes you might have been going 70. Sometimes you may have been going 10, depending on the neighborhood. So your average rate of change doesn't take into account those fluctuations. It just looks at your starting and ending point. Whereas your instantaneous rate of change, if you look down and you're going 70 miles per hour, that's the rate of change at that moment. So that's what we are trying to figure out. How much is something changing at this particular moment? And so when we do this, the way we start this process is by really considering what's happening at one particular point. Once we figured out how to do it for 1 point, we can generalize it to a function. But for right now, we're going to pick a point and we're going to see what we can do with that point. Okay, so our work sort of starts visually. We're going to start with a graph here to look at the process of how this might work. So this is the graph of the function 0.5x squared, okay? And I've decided that I want to approximate the instantaneous rate of change, okay? And I'm going to note that is IROC, instantaneous rate of change, just so that I don't have to write it out every single time. And I'm interested in what's happening at x equals -1. So that's the point that I'm going to focus on for our sort of conceptual understanding. So if I want to know what's happening at -1, so -1 is this point right here, right? So -1, I go up to the function. I want to know how quickly the function's changing at that point. Well, the only thing I know how to do right now is average rate of change. Right? That's the one tool that I have, slope of the line, right, between 2 points. So I'm interested in 1 point. So what I'm going to do is I'm going to take that 1 point and I'm going to pick a point to the left and to the right so that I can draw in secant lines to get an approximation, because that's the one thing I know how to do is find the slope of the line if I have 2 points. So what I want to do is I want to pick a point to the left and to the right, but that is the same distance from -1. So what I'm going to do is I'm going to pick the point -2. to -1, so 1 unit away, and -1 to 0, right? So what I'm doing is I'm looking for what's called an average rate of change to the left and to the right. So I'm picking a point to the left and to the right. So I'm going to do these separately. I'm going to start with the average rate of change to the right. And so to the right, I'm using the point -1 and 0. So I picked a point 1 unit away from the one that I'm interested in. I drew in my secant line, which is this line here. And now I'm going to do the average rate of change because that's the one I know how to do. So remember, with average rate of change, I'm doing f of b minus f of a over b minus a. So it looks like this in the formula. F of 0 means I'm going to go to the function at x equals 0 and find the y value. So that's 0 minus. Now I go to -1 because I need f of -1. So if I go here and I go up, I see that that is 0.5 divided by, now I have 0 minus -1. The minus and the negative are going to cancel. And I get -0.5. Okay, so the slope of the secant line to the right is -0.5. Okay. Well, that was an average rate of change to the right. Let's do it to the left, and then let's see what we can figure out about these numbers. So when I do it to the left, I use the point at -1 still, and then I pick something to the left. Since I went 1 unit to the right, I'm going to go 1 unit to the left to be consistent. So here I have f of -1 minus f of -2 divided by -1 minus -2. So again, f of -1 was 0.5. F of -2, I go all the way up here, and then I go all the way over here, I see that that's at 2, divided by, now again, be careful with your negatives here, that works out to be 1, and this gives me -1.5. Okay, so the slope of this line is -1.5. So what does that tell me? Right? What that tells me is that my instantaneous rate of change has to be on this interval. It has to be somewhere between -0.5 and -1.5 because of the way that the function changes, it creates these bounds, okay, for the actual instantaneous rate of change. So I can write it something like instantaneous rate of change has to be between, what did I say, -0.5 and -1.5. And when I say between, I also mean it could equal. It probably won't, but it gives us some bounds of where my instantaneous rate of change needs to be. So this is the process that we're going to do. We're going to be looking for average rate of change on the left and average rate of change on the right to help us get a good approximation of the instantaneous rate of change. Now, before we get into approximations, we also need to think about how we might make this approximation better. So what we're going to do is we're going to take this graph on this picture, and instead of going between -1 and 0 and -1 and -2, we're going to try it a little bit closer. What if we use -1 and -0.5 and -1 and -1.5? Will that change my bounds here? So we want to see what happens as we get closer, because remember last time when we talked about limits, we know that the closer we get to the thing we want, the better the approximation. Okay, so here's what I want you to try. So I want you to try to write out what this approximation is going to look like if we get closer. So now we're still interested in -1, but we're going to use what's happening at -0.5 and -1.5, which is closer to -1. Okay, so see if you can set up the left and the right hand approximation, just like we did in the last one. The numbers aren't quite as nice for your approximations, but do your best. We know at -1 that this is 0.5. So this is like half of 0.5, and this is sort of like half of that. So just approximate to the best of your ability. You're going to try the left and the right. Set it up the best you can. Feel free to check in with someone next to you. I'll give you about 2 minutes and then we'll go through it together and see what kind of impact it has to get closer to -1. All right, take about 30 more seconds to finish up wherever you're at. All right, so when we do our approximation to the right, by going between -1 and -0.5, we're a little bit closer to -1 this time. We're doing f of b minus f of a over b minus a, or change in y over change in x. So f of -0.5. So this is where we have to do a little sort of approximating of what that value is. You may not get the same exact number as me, but as long as we're in the same ballpark, then that's fine. So I got 0.125. So if you got 0.2, that's fine, right? 0.1, somewhere in there. Minus, and then f of -1, we said was 0.5 divided by, again, be really careful in the bottom, right? Because we have minus and negative. So that's going to give us 0.5 on the bottom. And when we crunch this number, we get -0.75. Obviously, if you approximate it slightly different than me, then this will be slightly different than mine. But if you get something between like 0.65 and 0.85, somewhere in that general range, that should be fine. So then we also want to approximate to the other side, which here is to the left. Again, we're using -1 and -1.5. So f of -1, we said was 0.5 minus. Now f of -1.5 is here. Okay, so we know it's a little bit bigger than 1. So I used 1.125. If you used 1.1 or 1.2, somewhere in that range, that's totally fine. Again, be really careful with your negatives here. Those are going to cancel each other out. And so here, that's 0.5. And when we crunch this number, we get -1.25. Okay, so again, remember the question we had was, if we get closer to -1, does that make a difference? Okay, so as a reminder, when we were 1 unit away, so in the last problem, our interval where we said the instantaneous rate of change had to be was between -0.5 and what was the other one? It was -1.5. So on a number line, that's what the interval was before, right? So we'll use some red lines here to mark it up. So now when we got closer to -1. Now we're between -0.75, which is to the left of -0.5, and -1.25, which is to the right of -1.5. So what that means is that our interval where the instantaneous rate of change needs to be is smaller, which means that this is a better approximation. So the conclusion here, and hopefully what you will understand from this exercise, is that the closer we take our approximation to the number we want, the smaller our interval and the better our approximation. So what we're going to be doing as we go is we're going to be working to make our approximation as good as possible by shrinking this interval as much as we can. So this is sort of a little bit of a spoiler alert here of what's going to happen. But eventually, not quite yet, but eventually what's going to happen is that if we get close enough to -1, the secant line on the left will have the same slope as the secant line on the right. And so they will join to make one line, right? Because if they have the same slope, they become the same line. That's what we're trying to get to. We're not quite there yet, but when that happens, right, we get what is called a tangent line. Okay, so remember before we had a secant line which connected 2 points, and now we are trying to get to a tangent line which only touches at 1 point. Okay, so a tangent line is a line that's going to touch our function at the given point, and the slope of the tangent line is the instantaneous rate of change. Okay, so it's exactly what we are trying to find in all of our examples. So let's go back here for a minute to the example we just did, and let's draw on our tangent line. I'm going to try to here. I don't have a ruler. I meant to have a ruler. Hold on. Use my notepad here. Okay, so I want you to notice that the slopes of the secant lines form these bounds because one is slightly bigger than the slope and one is slightly smaller. So we're trying to find this tangent line slope by approximating these slopes around it. Okay, that's our goal. That's what we're building up to. And those are the things we're learning how to make better. But ultimately, we are trying to talk about the slope of the tangent line. So the slope of the tangent line is the instantaneous rate of change at that point. So that's the tangent line at -1. If we were interested in the rate of change at, say, 1.5, we'd have to draw a tangent line over here at 1.5. Okay. All right. So let's practice trying to get average rates of change. So we're going to start with this example here. So consider that I have a tennis ball, and I'm going to throw it up in the air. And I have the ability to measure the height of this tennis ball in all the time in seconds and record it in this table. So at time equals 0, the ball is 6 feet off the ground. Now that makes sense because hopefully you can still hear me. I am 5'5". So if I let go of the ball up here, that's going to be about 6 feet, right? So I'm like throwing it directly up. After 1 second, the ball is at 9 feet. After 2 seconds, that's at 11 feet. After 3 seconds, it's at 12 feet. And then it starts to come back down. So at 4 seconds, it's at 10 feet again. So the ball's going straight up and then coming straight back down. Okay. So what we want to do with this data is we want to approximate how fast the ball is traveling when t equals 1. Okay. So we could do this for any number on the table, but we're going to do this for time equals 1. And so based on what we learned conceptually from the graph, what we want to do is we want to use the table to find the average rate of change to the left of 1. So we're going to use these 2 points. And the average rate of change to the right of 1. So these 2 points, because that is going to give us bounds for how quickly the ball is actually traveling. So I want you to take 2 minutes and I want you to do the calculation for the average rate of change to the left of 1. So using the 0.19 and 0.6, and also to the right of 1. So using the 0.19 and 2.11. Okay, take 2 minutes, jot those down, see what you come up with, and then we'll go through it together. All right, take about 30 more seconds. All right, so when we do average rate of change to the left, we're using the independent values of 0 and 1 here. So we're going to do f of 1 minus f of 0 over 1 minus 0. So f of 1 means we're going to take the functional value or the dependent value. So that's going to be 9 minus 6 divided by, and we know that 1 minus 0 is 1. So that gives me 3. And when I do this to the right, I'm using the values of 1 and 2. So 1 and the one directly to the right of it. So f of 2 is 11. F of 1 is 9 divided by 1 gives me 2. Okay. So let's take a pause here and talk about the units of what these numbers are, right? So think about this calculation here. This 9 and this 6 that we're subtracting on the top, these are from the dependent row, which is feet, right? So all the numbers on the top are talking about feet. And then on the bottom, the 1 and the 0, those are times in seconds. So directly correlating these numbers to where they are on the table helps us figure out the units here. So this is 3 feet per second. So as we start to look at rates, you'll find that we're going to have something per something a lot of the time because it's how quickly something is changing. So to the left, we are doing 3 feet per second is how quickly the position of that ball is changing. The same thing's going to happen down here, 2 feet per second, because again, the 11 and the 9, those are in feet, and the 2 and the 1 are in seconds. So we know that our instantaneous rate of change has to be between 3 feet per second and 2 feet per second, right? That's our little window of time. So there's sort of 3 ways we can talk about this approximation, right? We can say that we have a left-hand approximation, which is 3 feet per second. We have a right-hand approximation, which is 2 feet per second. But then we also have what's called the best guess or the best approximation. And so the way we get that is to take the left and the right and average them. So we would do 3 plus 2 divided by 2, right? And that's going to give us 2.5 feet per second. So sometimes on Wiley or on a mini quiz, we may say, you know, what is the left-hand approximation for the instantaneous rate of change? If we're asking for the left-hand approximation, it's 3, because that's the one where we did to the left. If we ask for the right-hand approximation, the answer would be 2. If we ask for the best approximation, that means you have to average them together, and we would get 2.5, okay? So as we mentioned before with limits and when we looked at the graph, the way that we would want to make this approximation better is to get closer to 1. Now we have a problem because we have a table here. So we don't actually have the ability to do anything with this table, right? We are as close as we could get, right? 0 is the closest to the left and 2 is the closest to the right. But if I could repeat the experiment, right, and I could record data more often, then I could get a closer approximation. So let's pretend hypothetically that I was able to conduct this experiment again. Okay, and now I'm able to record the height of the ball every half a second. I realize that this is not as dark as it should be. So first I want to point out that all the values for the integer numbers are the same as they were on the last table. That's what I'm tracing right now. So these didn't change. So at time equals 0, the ball is 6 feet off the ground. At time equals 1, it's 9 feet off the ground. At time equals 2, it's 11 feet off the ground. So that's the approximation we did last time between 1 and 0 and 1 and 2. But let's say that I now know that at 0.5, so at half a second, the height was 7.8, and that at 1.5, the height was 10.1. So now, if I want to approximate the instantaneous rate of change at 1, I have values that are closer, which is going to make my approximation better. So I would like you to do the left and the right-hand approximation around 1 with this new data. So to the left, you'll use 1 and the 0.5 data. And to the right, you're going to use 1 and the 1.5 data. But I want you to write that out and see what you get for both the left and the right. And if you have time, you can also do the best by averaging them together. I'm going to give you about 2 minutes to write it out, and then we'll go through it together. All right, take about 30 more seconds. All right, so let's see what happens when we get a little bit closer. So just as a reminder, in the last edition of the same problem, when we did the left and the right, we were going between 0 and 1 and 1 and 2. And we had 3 feet per second and 2 feet per second. So we knew we had to be between 2 and 3. That was our interval. But now we're a little bit closer. So when we do it from the left, so between 0.5 and 1, we're going to have 9 minus 7.8 divided by 0.5. So 1.2 divided by 0.5 gives me 2.4 feet per second. The units don't change, right? We just added more numbers here. So over here, and then when we do it to the right, we have the 1.5. So we have 10.1 minus 9 over 0.5. So that's going to be 1.1 divided by 0.5, which is 2.2 feet per second. So now we've gone from an interval of between 2 and 3 to an interval of between 2.2 and 2.4, right? So that interval is significantly smaller and more accurate to where our instantaneous rate of change needs to be. if we were going to do a best estimate, we would average these. So 2.4 plus 2.2 divided by 2 gives me 2.3 feet per second. Okay, so again, by getting closer to 1 by using the 0.5s, we were able to make a smaller interval of where our instantaneous rate of change needs to be, and we were able to get a better approximation, right? So we know it has to be between 2.2 and 2.4, so 2.3 is a better guess, because remember, our best guess before was 2.5, but now we know that that is out of the actual interval, right? It's got to be between 2.2 and 2.4. So ultimately, you know, if we were able to get super close, right? If we were able to measure time in 1/100th of a second, which is pretty crazy, but let's say we were able to do it, and we were able to get the height at those times, then we'd be able to get an approximation that was really, really close. And so if we were to do this, right, and we were to do f of 1 minus f of 0.99 divided by 1 minus 0.99, right? So if you put that on your calculator, you end up with a left-hand approximation of 2.3645. And then similarly over here, if we were able to get super duper close, you end up with 1.01 minus 1. If you put these decimals into your calculator, this one also comes out to be 2.3645. So this is accurate to 4 decimal places, right? So we have something that to 4 decimal places is the same from the left and the right. So what that tells me is that my instantaneous rate of change is 2.3645. Okay, how accurate you need to be really depends on what you're trying to model and why. I think our approximation up here was pretty good by getting within 0.5. But obviously this is a better approximation because now we're within 0.01, right? But what the idea here is that what's happening is as we get closer and closer to 1, even though we're doing the same type of calculation, it creates bounds that are better and better for our approximation. Okay, so that's what we're going to be trying to do. We are trying to get as close as we can to the point that we're interested in so that we can get the best approximation possible. Okay, so we have to take like a sidestep for a minute and circle back and talk about some wording and some notation for what we're doing. And so I want to give you just sort of a little background on why we need to do this. So back in the late 1600s, Isaac Newton and Gottfried Leibniz were both working on calculus at the same time, right? Like it was a big deal. They had big hair, all that stuff. So there was a lot of controversy on who actually discovered calculus first. They actually did it in slightly different ways, but there were similarities. And so Newton accused Leibniz of stealing his work because he had presented it somewhere, but Leibniz claimed he wasn't at that presentation, but Newton had never published it. I don't know, the 1600s were really dramatic. I don't know, people were still like witches back then. So basically it never got settled, right? In the mathematics community, no one ever really picked a side. And so what that means for us is that we have 2 sets of wordings and notations for the same thing because these 2 men did it separately and they called them different things. So even though they mean the same thing, we have 2 sets of everything. So depending on if you're looking at it in physics or in math or, you know, in business, the notation will really just depend on what you're looking at. So I want to make sure that we know both sets of notation and wording so that no matter how you see it, you know that we're talking about the same thing. So the wording that we've been using so far, instantaneous rate of change. The other word that we use to talk about this is the derivative. Okay, the derivative is the instantaneous rate of change. Okay, these mean the same thing. I think instantaneous rate of change is more descriptive of what's happening, but derivative is the common word that you will hear for what we are doing. We are finding the derivative. So if you hear me say or someone else say, oh, what's the derivative? That means what is the instantaneous rate of change? Those words mean the same thing. Now, in terms of how we notate this mathematically with symbols, right? Because we often write things with symbols here. You're going to see f prime of a. So it looks like this. This little comma up here or apostrophe, we say the word prime to indicate that it's a derivative. So this is what's called the first derivative because there's one of these, okay? Later on, not today, but later, probably next week, we'll look at the second derivative and there's two of these, okay? We don't need to worry about that yet, okay? We'll worry about that later. For now, everything we're talking about is called the first derivative. So the rate of change of the original function. A is the value we're interested in. So for example, when we were doing this last problem, we were looking for f prime of 1. What is the instantaneous rate of change at 1? That's the number we were basing everything off of. Okay, so this notation with the prime, that's Newtonian notation, and that's what we use most of the time. The other way that you'll see this, and this will come up in 2.3, so we'll circle back and talk about it again, is dy dx. So this means the derivative of y with respect to x, and this means the same thing as the prime, okay? So both of these are telling you that we're finding a derivative. Like I said, the majority of the time, we're going to be using this notation, f prime of whatever the number is, but this is particularly helpful when we explore units in 2.3. So we'll bring this notation back to figure out why the units are what they are. They make more sense when you think about them with this notation, but these mean the same thing, okay? So that's our quick lesson on wording and notation. Again, these all mean the same thing. So hopefully we'll get comfortable with all the different ways that it comes up. Okay, so let's put some of this back into practice here. We want to use some notation. We want to do some calculations. We want to sort of throw it all together and see what shakes out. So here I have a table that has values for 1, 2, 3, 4, and 5. And I want you to use this table to approximate the instantaneous rate of change for every single point. Okay, so how do we start this? The first thing you're going to want to do is you're going to want to find the average rate of change between every single set of points. So between 1 and 2, between 2 and 3, between 3 and 4, and between 4 and 5. Okay, and then we'll use that to get our best approximation, right, for the middle values by averaging. But you want to start by finding these rates of change in between the points down the table, just like we did in the last couple of tables. Okay, so take 2 to 3 minutes, see if you can get those figured out. Once you have the average rates of change in here, you can notate it. This is how we're going to write it. So f prime of 1, what do we think that's going to be? F prime of 2, what do we think that's going to be based on the table, right? So on and so forth for all the values. Okay, try it out. Feel free to talk to someone next to you. We'll go through it together in about 2 to 3 minutes. Okay, take about 30 more seconds. All right. So what I did here is I just sketched out the average rate of change between each set of points here. So remember, you're going to do the change in y over change in x, or the change in the dependent values over the change in the independent values. So the average rate of change between 1 and 2 is 9, between 2 and 3 is 15, between 3 and 4 is 21, and between 4 and 5 is 27. So now we need to take these numbers and figure out how to approximate the derivative at each of these values. So we start with 1. So what I want you to notice about 1 is that we don't have a left-hand approximation. We don't have any way of getting any information about what's happening at 0 because we only have what's given to us. So that means if we want to approximate the derivative at 1, we have to just use the right-hand approximation because that's the only one available to us. So that's going to be our best guess for what's going on at 1. When we do the derivative at 2, however, you'll notice that we have a left-hand approximation and a right-hand approximation. So our best guess here is going to be to average those two values together. So we have 15 plus 9 divided by 2. That's going to give me 12. So my approximation for the derivative at 2 is going to be 12. Now, if we do this for 3, we see that at 3, we do have a left and a right, right? So we have the left hand of 3 and the right. So we have 15 plus 21 divided by 2, right? So we're going to average those together, and that's going to give me 18 as my approximation here. F prime of 4, so the derivative at 4 is going to have a left and a right. So I'm going to be able to average those together. So 21 plus 27 divided by 2, that's going to give me 24. And then last but not least, if I approximate at 5, I run into the same problem that I had with 1. I don't know what's happening to the right of 5, and so I can't do a right-hand approximation. So the best guess I have is just the approximation to the left, because that's the only information I have. So that gives me 27. Okay, so that's how we normally approximate derivatives on a table. I do want to tell you about a shortcut that you can use here. If you want to make your work a little bit easier, I'm just going to pick one to do, but this will apply to any value in the middle of the table where you're going to have a left and a right. So let's say I wanted to approximate the derivative at 2. I know that the value is going to be 12, but instead of doing a left hand and a right hand and then averaging them, I can actually do the average rate of change around 2 by using the values, the point directly to the left and the point directly to the right. So what that would look like is I would use 31 minus 7 divided by 3 minus 1. Okay, so I just use the values directly next to 2, and I'm doing the average rate of change calculation, right? And that's going to be 24 over 2, which also gives me the 12. So you can do it this way. So if you have a table and you're on a mini quiz and it says something like approximate the best value of f prime of 2, you can use the two values next to it to do just one calculation, or you can do the left and the right and average them. It'll give you the same exact number every time. Okay, so that's just a little shortcut if that's helpful. You don't have to do it that way, but you can if you'd like. So now that we're sort of starting to get comfortable with notation, one thing I want to sort of circle back to is connecting this to the slope of the tangent line. So what I want to point out here is we don't know what this function is, right? But if we had a picture of this function, what does it mean to have f prime of 1 be approximately 9? What that means is if we were to go to our function, we were to go to x equals 1, and we were to draw in a tangent line, the slope of that tangent line would be 9. That's how quickly the function is changing at that point. If we were to draw in a tangent line at 4, the slope of that tangent line would be 24. So that's steeper than 9, right? So these values are telling us the slopes of the tangent lines that touch at these points, okay? So that's going to lead us into our next activity, which is one of my favorites, and I don't know why, but you'll see that this will show up on some of your future quizzes. It's a game I like to play called, is it positive, negative, or zero, right? And so what we want to do is we want to think back and make sure we are connecting this to the tangent line. So we'll do one of these together, and then I'll have you try the others. But there's 5 derivatives here: f prime of -2, f prime of -1, f prime of 0, f prime of 1, and f prime of 2. And for each of these, I want you to try to determine, is this going to be a value that is positive, negative, or 0 based on the graph? So how do we figure that out? Well, the way that we figure it out is we have to try to visualize the tangent line, right? So let's do one together so you can see what I'm talking about. So f prime of -2. That means I need to find -2 here, which is right here, go to my function, okay, and then visualize what the tangent line is going to look like. So the tangent line is going to look something like this. And so because this is downward sloping, it goes down from left to right, I don't know the value of the slope, but I know it has to be negative, right? It's got to be negative because the slope is going down from left to right. If when you visualize the tangent line, it's going up from left to right, the slope will be positive. Therefore, the derivative will be positive. And it will be 0 if that slope is horizontal, okay? So these are by halves. So this is -1, -1.5, -2, positive 0.5, 1, 1.52. So I want you to think about each of these values. Just look at the picture and try to take a guess whether you think the slope of the tangent line is going to be positive, negative, or 0. Okay, so I'll give you a minute. Just think about it, jot it down what you think it might be, and then we'll draw in the tangent lines and check. All right. So I cannot stress enough how important it is that we remember that the derivative is the slope of the tangent line, right? So that is directly related. That is how we are finding this approximation, as we are approximating the slope of this tangent line. So let's go ahead and look at -1. So if I go down to -1 and I think about what the tangent line would look like, it's going to have this general shape to touch at one spot. And so that's going upward from left to right. So the slope of this line is positive. So this goes back to what I was saying, is I assume you know everything about lines. So I assume that if you look at a line, you know whether the slope is positive, negative, or 0. If that's something you don't know, it might be something you need to practice a little bit to get comfortable with this, right? So here, f prime of 0, we come over here to 0. When you draw on the tangent line, this one happens to be horizontal, right? It sits right on top of that hill. And so a horizontal line has a slope of 0. So whenever we end up with one of these that just lays almost flat like this, we know the slope is going to be 0. When we go to 1, right, that's right here. We draw on this tangent line. We can see it touches just like this. So this is going downward from left to right. So if it's moving in the downward direction, the slope here is going to be negative. So that means f prime of 1 has to be negative. And then finally, f prime of 2, right? I go to 2, I draw my tangent line. I can see that's pretty steep, but it's steep in the upward direction. So that's going to be positive. Now, at another point in time, I can't remember if it's the next class or 2.4, we're going to learn how to approximate the value that goes with this. So we know this is positive, but we don't know if it's positive 10, positive 20, positive 30. We're building up to that. But the first thing we want to do before we find the actual value is just have a sense of if the value should be positive, negative, or 0. So this is like a first step in helping us to reconnect back to the tangent line. Okay, so now the last part of things we need to make sure we can do here. We've done this with tables, we've done it with graphs, and now we need to really understand how we do this with functions. So here we have the function 4x squared, and we're interested in finding the instantaneous rate of change at x equals 3. So we want to know how quickly this function is changing at 3. We could also write this as find f prime of 3. So thinking back to what we know from the table examples and from the graph examples, we know that we want to find the average rate of change to the left and to the right, and that we want to get close to 3. So how do we start this and how do we set it up? I'm going to give you a few tips and then I'm going to let you try this. So what we want to do here is we want to set up our own table, right? That's the easiest way to organize what we're doing. And so what we want to do is we have our value that we're interested in, 3, right? That's in the problem. We're going to plug 3 into the function. So 3 squared is 9. 9 times 4 gives me a dependent value of 36. So we want to pick something a little to the left and a little to the right, remembering that the closer we are, the better our approximation. So I'm going to let you pick what you're going to pick to the left and the right, but you want to pick the same distance, right? So however far you go to the left, go to the same distance to the right. Once you pick the number you're going to use to be close to 3 on the left, you have to plug it back into the original function to get the dependent value. Once you have those, you're going to do the average rate of change to the left and the average rate of change to the right. And that will help give you bounds so that you can make a good guess about the best approximate value for the derivative. Okay, so I'm going to give you about 3 minutes to work through this. Then we're going to talk about wording and the differences in how we word these types of problems to make sure that we're getting the right approximations. Okay, so try it out. Pick your values to the left and right of 3, find the dependent values, then do average rates of change. And then we'll go through it together really soon. Take about 30 more seconds. All right. So when I did this out, I picked the values 2.99 to my left and 3.01 to my right. You may not have picked the same numbers as me, and that's okay. You might have done 2.9 and 3.1. You may have even done 2 and 4. But obviously, if you pick different numbers than me, then your approximations will be slightly different than mine, right? But the idea is that we really do want to get close to 3. So I do recommend that you do something like 2.9 or 2.99, just so that you don't have to repeat if you're not quite close enough. So once you have those numbers picked out, you plug them into your function to generate your table, right? So again, you're plugging those into the original, you generate your table, and then you do the average rate of change on the left and the average rate of change on the right. So seeing these values from the left and the right, I'm pretty confident to say that my derivative here is approximately 24. Those are both close to 24, and I'm just picking a whole number because that's the easiest here. And so I have a good approximation of what's going on. But let's talk for a minute about the way that we might ask you this in a different way on a quiz or on homework, so you can recognize exactly how to do what we're asking you to do. So in this instance, the way it's worded, this is exactly what we would do. We're approximating the instantaneous rate of change. And unless it says left or right, you're really going for the best approximation. So something in between them, right? However, we could say approximate the instantaneous rate of change to the left using delta x equals 0.01. So what does that mean? That means that we want you to do a left-hand approximation only, so something slightly to the left of 3, and that amount that we want you to change from 3 to the point next to it is 0.01. So that would be 2.99, right? And so that means that the answer here would be 23.96. It would be exactly just the left-hand approximation because we're specifying the left and we're telling you exactly how far to go, right? Similarly, we could do something like to the right using delta x equals 1. So that would mean that I would need to use 3 and 4, because 4 is 1 unit to the right. And so then I'd plug in my 3, I would get 36. I'd plug in a 4, which would give me 64. And then I would do the average rate of change here to the right using delta x equals 1. So that would give me 28, right? So if you have conditions in the problem saying left or right or a specified amount to go, you have to do it that way to get the right answer. You can't just do whatever approximation you want. When you can do the approximation you want is if it's just a general approximate this value. If there's no left or right qualifiers, then you get to pick how you want to set it up so that you can get a good approximation. Okay, so be really careful about the wording here. So I think I'm going to skip example 4 because I think example 5 will be a little bit more helpful for your homework, but I will tell you example 4, you're going to do the same exact way as example 3. You're going to set up a table where t is going to be equal to 2, and then you're picking values near 2, and you're just plugging it into this function. So you'll do it the same way. But let's skip down to example 5. So suppose that we know for the function below that f of 4 equals 25 and f prime of 4 equals 1.5. Use this information to find the coordinates for points A, B, and C. Okay, so one of the things I want you to notice here is that there's no vertical scale, right? So there's nothing drawn in. So the really only information we have about the vertical scale is this one piece of information here. So what this information tells me is that when the independent variable is 4, the dependent value is 25. But if you look at the picture, the point A is the point that we're talking about when the independent variable is 4. So that tells me that the point A is going to be the point 4, 25, right? So that's from the setup. I didn't have to do any calculations to figure that out. Now, points B and C are on the tangent line of this function, okay? C kind of looks goofy, but it's on the line, okay? So that's at 3.9 and 4.2. So I need to figure out what I know about the tangent line to try to figure out what's going on with points B and C. So the second piece of information that I have here is that f prime of 4 equals 1.5. So that tells me the slope of the tangent line at x equals 4 is m equals 1.5. Okay, so the slope is m. So here, 4 is where this tangent line touches. So this information is talking about this line because it touches at 4, and this information is about 4. So the slope of this black line here is 1.5, okay? Because the derivative tells us the slope of the tangent line. So what I want to do is use all this information to get the equation of this tangent line. So a tangent line is a line, so it's always going to have that form y equals mx plus b. So I know that the m is 1.5 from the setup. So y equals 1.5x plus b. So the only piece of information that I'm missing is that b value. However, notice that a is also on this line. And so A, I know that point from the setup, so I can plug that in for x, y to get the value of B. So if I plug that in, I'm going to plug in 4 for x and 25 for y. So 25 equals 1.5 times 4 plus B, right? So 4 times 1.5 is going to give you 6. So we are going to subtract that over to the other side. If you subtract 6 from both sides, you're going to get B equals 19. So the equation of this line is y equals 1.5x plus 19. So how does that help us figure out our other missing points? Well, we know the x coordinate for C and the x coordinate for B. So all we have to do is plug that coordinate in to x to get the corresponding value for y. So here for B, the x coordinate is 4.2. If you take 4.2 and you plug it into your equation of the line, you are going to get a y value of 25.3. Again, I took the value for x from down here and plugged it into the equation of the line. Similarly, for point C, I know that the x value is 3.9. If I plug that into my equation for x, I'm going to get a y value of 24.85. So what is the process here? The important piece here was finding the equation of the tangent line, because once I have the equation of the tangent line, I can plug in the values to get these points. So to get the equation of the tangent line, I needed to use y equals mx plus b, and m came from the derivative. So again, we're trying to connect the slope to the equation of the line. And so we're doing that by understanding what this information is telling us to get this equation of the line. Okay. So I think we'll stop here for today. On Thursday, we will be going over the derivative function. So we're going to generalize this a little bit. But otherwise, just make sure you don't forget about your mini quiz on Wednesday.